right? Design the shear flow, right? So this is known as design of the shear flow, right? For box, and the wooden structure is to distribute the shear flow, and the nail is to transmit the load. That is why for this case, the fastener, you don't consider the what? You don't consider the web. That is why you don't consider the what? The web. Are we clear? Okay. Let's look at another interesting problem. Okay. Let's look at another interesting problem. Okay. Let's look at another example. Yeah, example number 2. Okay. So example number 2. Okay. Copy. So this is the example that we're going to go through. Oi, Eugene, what are you doing? And I'm going to get a figure. And I'm going to come here. Okay. Example number 2. So if you have the image of the handout, okay. So the box beam, there you go. You can see it's constructed from 4 boards. They are fastened together using nail spacing along the beam every 2 inches. Okay, so the spacing is every 2 inches. If each nail can resist a shear of 50 pounds, okay, determine the highest V that can be applied to the beam without causing failure to the nails. Okay, without causing. So we're going to, so this is a structure, okay? So I'm going to write, so if we look at the structure, we draw our transformation, right? So this is our Y, this is Z, and this is our X direction. Okay, so this is so our IZZ, okay, so IZZ, right, is equal to, is equal to 197.7 inches to power of 3. So that is your IZZ. Okay. So next we are going to look at the force resistance of the nail, or the resistance force. Of the nail. So it's equal to 50 pounds. And we are given the spacing, which is equal to 2 inches. So every 2 inches, they put the nail in. Okay, every 2 inches they put the nail in. Okay. So we're gonna come. So we're gonna look at the structure now. Okay. So the structure. I'm just going to quickly sketch out. Okay. So this is our structure. Okay. So this is a very quick sketch. Okay. So this is our. So the nails are going through here. And then are going through here. Right? This is how the nails are going through. And then we have our VY. Okay. Then I'm going to, there's a centroid. Okay. So for this question, actually, you also have to find the centroid. You guys know to find the centroid. I don't want to waste time. All right. So from the top, 2.1 inches. Okay, so that is the position of the centroid. Okay, so we're going to look at we're going to call it this the top flange. And then we can call this the bottom flange. Now why this example is very interesting is we are going to integrate what I teach you down here together with our what? 4 rules. Okay, together 4 rules. Okay, now. So we are going to look at, we're going to calculate Q first. Q is common at the top and bottom. Okay, so Q, let me see if I can move this figure a bit upwards so I have more space. Right. Okay. So Q, okay, I'm going to split this into 2. So Q is equal to resistant force, right, of nails divided by spacing, right? So this is equal to 50 multiplied by 2. Why 2? Because you have left, right, and right. Yes or no? You look at the top or at the bottom, you have left and right nail, and then you divide by the spacing. The spacing is equal to 2 inches. Okay, so this will be equal to 50 pounds per inch. Okay, that is straightforward, right? Okay. So now, the failure can be at 2 parts. It's either at the top flange or the bottom flange. I don't know which one. Okay, this is where we don't know which one. We have to check. Okay, we have to check. I don't know whether it's the top or the bottom. So if you look at the shear flow, how is it going to flow? It's going to distribute this way. Shear flow always use ping. Okay, so it is declared that this beam is a what? It's a box beam. Okay, so we have to, it's declared as a box beam. We have to use box beam analysis, right? Later on, I'll teach you how to identify whether it's box beam or otherwise. So based on the ping, you see this is how the shear flow will flow. Okay, right. So the top flange is easy, yes or no? Okay, so we're going to look at top flange. Right. So we know the top flange will distribute the load, right, to the what? To the nails. That is why for the top flange, you only calculate first moment of area, you only calculate here. Right, the shear flow will distribute, and then the nails will what? Will transmit to the flange. Okay. Does that make sense? Does that make sense now? Yes or no? Top flange of the top flange failure. Does that make sense what I'm trying to tell you? Hello? Hello? Nothing. Oh, shoot. So Q for top flange, right, is equal. So we look at the width is 12 inches. The depth is 1 inch, right? And then this is equal to the Y bar is 3.1 minus by 1 divided by 2, right? Half. So this will be equal to 3.1.5 times 12. So this is equal to 31.2 inches cube. Okay. So now we have, so the next formula we're going to apply is Q is equal to VQ over I. So this will be equal to 50 is equal to V, and multiplied by Q is 31.2. Okay, it's 31. My 3 is looking very bad. Okay, multiplied by 31.2 divided by I. So I is equal to 197.7. So the V based on top flange failure is 50 times 197.7 divided by 31.2. So it's equal to 316.8 pounds. Okay. So now you guys are going to go crazy. Bottom flange failure. So the failure is either at, I'm going to highlight, okay, where there is joint. It's either here or here, the nails at there, or over here. Now, which first moment of area to take? Confusing, isn't it? I hear no answer. Where do you get 3.0? Oh, the 3.1 was given. Okay. So in real life, you have to find it. Okay. In a exam question, you have to find it. Because I don't want to repeat again and again how to find centroid and second moment of area. Okay. Okay. So to find centroid, you can look at last week's notes. I did do that. Okay. So now, bottom flange. So if you look at the arrow, right? If you just obey the arrows you see now, if you just obey the arrow, you say, Eugene, since the arrow is there, I think I'm going to take this. Yes or no? Right? Yeah, the answer is no. Wei Ming, you're right. Why no? Rule number 4. You're going to start your analysis from Y variable max. Right? You are going to, now you don't look at the direction of the what? You don't look at the direction of the pink arrow. The pink arrow comes to here, right? So you are now, the right thing to do is to consider this what? This wooden section. Not the web. Okay. I understand that the web will still transmit the load, right? To find the shear flow of the structure at the bottom, you just need to consider the what? The bottom flange. Because where it's going to fail is the load that's transmitting into the what? Into the bottom flange. Okay, so remember the analysis start from outside, from Y max to go into the what? Into the centroid. So for this case, you just need to consider the bottom flange. You don't need to consider the web because the web is not going to fail because of the nail, right? Is there any nail at the web? No, right? The nails are more nailed into the what? Into the flange section, right? So the confusing part is people will look at it. The nails are vertical and horizontal. Whether the nails are vertical or horizontal does not matter at all. Okay, it's how the shear flow has been distributed. Okay, so for this case, at the top is easy, right? At the top, you say, okay, this is the direction, right? It's straightforward. Now this is coming in, and when it's coming in, it's coming in from the what? From the web, right? No, you just need to consider the flange because rule number 4 say we have to look at Y max. So what do I mean by rule number 4 is look at Y max? So when Y max goes back up to this position, you only need to cover the entire area of the what? Of the flange. Okay, someone has unmute, so he or she has a question now. Anyone? No? Okay. So now we are going to calculate the Q bottom flange. Okay, so the width, so bottom flange, the width is equal to 6, right? The depth is equal to 1, and then the Y bar, so we know from here to here, right? From here to here is 3.1. Sorry, we know from here to here is 3.1. So we know half of here is 0.5. We all need to do to find it. So 5 plus 1 plus 1. This plus 1 plus 1, the whole thing, minus by 3.1.